Hello and welcome back to Introductory Astronomy. As our field of view expands to truly cosmic scales, the focus of our studies shifts dramatically. Planets become inconsequential. Stars themselves mere points of hydrogen consumption. Now entire galaxies become the quote-unquote atoms from which the universe is built. Distant realms completely unknown to scientists just a century ago. We now know of literally millions of galaxies beyond our own. Most are smaller than the Milky Way, some comparable in size, and a few much larger. Many of them are sites of explosive events far more energetic than anything ever witnessed in our own galaxy. All are vast gravitationally bound assemblages of stars, gas, dust, dark matter, and radiation separated from us by almost incomprehensibly large distances. The light we receive tonight from the most distant galaxies was emitted long before the Earth existed. By studying the properties of galaxies, we gain insight into the history of our own galaxy, and of course, the universe in which we live. Looking at the opening image here, we have a double image superposing optical light acquired by the Hubble Space Telescope in Earth orbit on radio emission captured by the Very Large Array in New Mexico. At center in white is a giant, visible elliptical galaxy cataloged as NGC 1316, which is probably devouring its smaller northern neighbor. The result is a complex radio emission in orange called Fornax A, spanning more than 1 million light-years of space. In this chapter, we're going to talk about Hubble's galaxy classification, the distribution of galaxies in space, Hubble's law, active galactic nuclei, and the central engine of an active galaxy. Let's start with Hubble's galaxy classification. In frame A, we have a collection of many galaxies, each consisting of hundreds of billions of stars. This one is called the Coma Cluster, and it's a group of galaxies more than 100 million parsecs from Earth. The blue spiked object at top right is a nearby star. Virtually every other object in this image is a galaxy. In frame B, it's a recent Hubble Space Telescope image of part of that cluster. Spiral galaxies are classified according to the size of their central bulge. Variation in shape among spiral galaxies is demonstrated in the pictures on this slide. As we progress from type SA to SB to SC, so from left to right, the bulges become smaller and the spiral arms tend to become less tightly wound. Type SA has the largest central bulge. Type SB is smaller, and type SC is the smallest. Type SA tends to have the most tightly bound spiral arms, with types SB and SC progressively less tight, although the correlation is not perfect. The components of spiral galaxies are the same as in our own galaxy: disk, core, halo, bulge, and spiral arms. Here we have the picture of the Sombrero Galaxy. It's a spiral galaxy seen edge on. Its official classification is M104. This galaxy has a dark band composed of interstellar gas and dust. The large size of this galaxy's central bulge marks it as type SA, even though its spiral arms cannot be seen from our perspective. The inset shows this galaxy in the infrared part of the spectrum, highlighting its dust content in false-colored pink. Here's an illustration of variation in shape among barred spiral galaxies. The variation from SBA to SBC is similar to that for the spirals in figure 24.2, except that now the spiral arms begin at either end of a bar through the galactic center. In frame C, the bright star is a foreground object in our own galaxy. The object at top center is another galaxy that is probably interacting with NGC 6872. So what classification is our own galaxy? Our Milky Way galaxy is an SBC, so it is a barred spiral galaxy of type C with about 300 billion stars. Elliptical galaxies have no spiral arms and no disk. They come in many sizes, from giant ellipticals of trillions of stars down to dwarf ellipticals of less than 1 million stars. Ellipticals also contain very little, if any, cool gas and dust, and they show no evidence of ongoing star formation. Many do, however, have large clouds of hot gas extending far beyond the visible boundaries of the galaxy. Ellipticals are classified according to their shape from E0 to E7, where E0 represents almost spherical and E7 the most elongated. In frame A, the E1 galaxy M49 is nearly circular in appearance. In frame B, we have M84, which is a slightly more elongated elliptical galaxy with classification E3. Both galaxies lack spiral structure and neither shows evidence of cool interstellar dust or gas, although each has an extensive X-ray halo of hot gas that extends far beyond the visible portion of the galaxy. And in frame C, we have galaxy M110, which is a dwarf elliptical companion to the much larger Andromeda galaxy. In frame A, we have an S0, or lenticular galaxy. Lenticular galaxies contain a disk and a bulge, but no interstellar gas and no spiral arms. They're in many respects intermediate between E7 ellipticals and SA spirals in their properties. In frame B, we see an illustration of SB0 galaxies, which are similar to S0 galaxies, except for a bar of stellar material extending beyond the central bulge. We also have irregular galaxies, and as you can imagine, they come in a variety of shapes. The small and large Magellanic clouds are close neighbors to our own Milky Way. They're prominent features of the night sky in the southern hemisphere. They're named for the 16th century Portuguese explorer Ferdinand Magellan, whose around-the-world expedition first brought word of these fuzzy patches of light to Europe, and they're dwarf irregular galaxies, gravitationally bound to our own Milky Way galaxy. So they orbit our galaxy and accompanied it on its trek through the cosmos. In frame A, we see the clouds' relationship to one another in the southern sky. Both the small, in frame B, and the large, in frame C, Magellanic clouds have distorted, irregular shapes, although some observers claim they can discern a single spiral arm in the large cloud. Some irregular 2 galaxies. In frame A, we see the strangely shaped galaxy called AM0644741, which is most likely plunging headlong into a group of several other galaxies, 2 of them shown here, which causes huge rearrangements of its stars, gas, and dust. In frame B, the galaxy NGC 1569 seems to show an explosive appearance, probably the result of a recent galaxy-wide burst of star formation. Here's a table of a summary of galaxy properties by type. And you can go through that on your own. So we have three main types of galaxies: the spirals and the barred spirals, the ellipticals, and the irregulars. Let's talk a little bit about Hubble's tuning fork. This is a diagram of Hubble's tuning fork that shows the basic galaxy classification scheme. We have the placement of the four basic types of galaxies: ellipticals, spirals, barred spirals, and irregulars. And the way they were placed in the diagram is suggestive, but the tuning fork has no physical meaning. It's just a representation of the classification. Here we have a sequence of 6 snapshots that chronicles the periodic changes in a Cepheid variable star in the spiral galaxy M100, which is a member of the Virgo cluster of galaxies. The Cepheid appears at the center of each inset, taken at the different times indicated during 1994. The star looks like a square because of the high magnification of the digital CCD camera, which is why we're seeing individual pixels of the image. The 24th magnitude star varies by about a factor of 2 in brightness every 7 weeks. Remember, Cepheid variables do that. So do RR Lyrae stars. Now, some galaxies have no Cepheids, and a lot of them are further away than 25 megaparsecs. So a good question would be, how do we figure out how far away a galaxy is? So we came up with new distance measurements. We have what is called the Tally-Fisher relation, which correlates a galaxy's rotation speed, which can be measured using the Doppler effect, to its actual luminosity. We know that a galaxy's rotation causes some of the radiation it emits to be blue-shifted and some to be red-shifted, relative to what the emission would be from an unmoving source, an observer. From a distance, when the radiation from the galaxy is combined into a single beam and analyzed spectroscopically, the red-shifted and blue-shifted components combine to produce a broadening of the galaxy's spectral lines. The amount of broadening is a direct measure of the rotation speed of the galaxy, such as the one at the right, NGC 4603, which is about 100 million light-years away. Type 1 supernovae all have about the same luminosity, as the process by which they happen doesn't allow for much variation. So they can also be used as standard candles. Standard candles are objects whose absolute magnitude is known and which can therefore be used to determine distance using their apparent magnitude. With these additions, the cosmic distance ladder has been extended to about 1 gigaparsec, that is 1 billion parsecs. So let's take a look at our ladder. It's an inverted pyramid that summarizes the distance techniques used to study different parts of the universe. The techniques shown in the bottom 4 layers, radar ranging, stellar parallax, spectroscopic parallax, and variable stars, take us as far as the nearest galaxies. To go further, we must use new techniques, for example, the Tally-Fisher relation and the use of standard candles, based on distances determined by the 4 lowest techniques. So we build from one to the other, like a type of ladder. Now, the Milky Way galaxy is part of what we call the local group, which is made up of nearly 50 galaxies within about 1 megaparsec from our own galaxy. Only a few are spirals. Most of the rest are dwarf elliptical or irregular galaxies, and only some are shown in these pictures here. Spirals are colored blue, ellipticals pink, and irregulars white, all of them depicted approximately to scale. The inset map on the top right shows the Milky Way in relation to some of its satellite galaxies. The photographic insets, top left, show two well-known neighbors of the Andromeda galaxy, M31. Those neighbors are the spiral galaxy M33 and the dwarf elliptical galaxy M32. Now, whenever we have a group of galaxies that's held together by its own gravity, we call that a galaxy cluster, just like we have star clusters. The central region of the Virgo cluster of galaxies, which is about 17 megaparsecs from Earth, contains about 3,500 galaxies. Many large spiral and elliptical galaxies can be seen. The inset shows several galaxies surrounding the giant elliptical known as M86. An even bigger elliptical galaxy, M87, noted at the bottom, will be discussed later in this chapter. Here we have the galaxy cluster Abell 1689, which contains huge numbers of galaxies and resides about 1 billion parsecs from the Earth. Virtually every patch of light in this photograph is a separate galaxy. Thanks to the high resolution of the optics on board the Hubble Space Telescope, we can now discern, even at this great distance, spiral structure in some of the galaxies. We also see many galaxies colliding, some tearing matter from one another, and others merging into single systems. Which brings us to Hubble's law. Let's talk a little bit about universal recession. All galaxies, whichever direction we look at, seem to be moving away from us. And the redshift of their motion is correlated to their distance. So right here we see optical spectra, shown at the left, of several galaxies named on the right. Both the extent of the redshift, which is denoted by the horizontal red arrows, and the distance from the Milky Way galaxy to each galaxy, so those are the numbers in the center column, they increase from top to bottom. The vertical yellow arrow in each spectrum highlights a particular spectral feature, a pair of dark absorption lines. The horizontal red arrows indicate how this feature shifts to longer wavelengths in spectra of more distant galaxies. The white lines at the top and bottom of each spectrum are laboratory references for those wavelengths. And here we have plots of recessional velocity against distance. In frame A, this is data for the galaxy shown in the previous slide, figure 24.16, and in frame B, it's a plot for numerous other galaxies within about 1 billion parsec of Earth. And as you can clearly see, there is a pattern there. Let's talk a little bit about the Hubble law. Hubble was the first to realize that the recessional velocity, meaning how far away, how quickly galaxies are moving away from us, is proportional to their distance, how far away they are from us. And he came up with this formula, V sub r is equal to h naught times d, where h naught is known as the Hubble constant, which is 70 kilometers per second per megaparsec. Now, applying this formula is very good, but it works better on further away objects. That way, random motions are overwhelmed by the recessional velocity. This puts a final step on our distance ladder. So we can use the idea of Hubble's law, that proportionality formula, for objects that are beyond 100 million parsecs. And it works great. And Hubble's law sits on top of our hierarchy of the distance measurement techniques. We covered 24.1 through 24.3. You should be able to describe the basic properties of normal galaxies and understand the extragalactic distance ladder and Hubble's law.